All right, so as we mentioned at the end of class last time, today we're going to start language translation principles. So we're going to skip ahead and do chapter 7, skip chapter 6 for the time being so that you can get started on your big project. So the topic here is language translation principles, and I have a question for you. What is the fundamental question of computer science?
What can be automated?
Oh, you guys are good. What can be automated? The fundamental question of computer science is what can be automated. And what big project are you going to work on?
Translation, building an assembler.
Yes, and that is a translator. So, obviously, we don't want to hire a bunch of assembler clerks to do the translating for us. So on our first slide here, the fundamental question of computer science is what can be automated, and one of the answers is translation from one programming language to another. So in order for us to approach, to attack this problem of automating the translation of a language, we need to understand what a language is. Now there's two kinds of languages: natural languages and artificial languages. Natural languages are, for example, English, German, French, Spanish. Those are natural languages. Artificial languages are languages that are defined by, are languages that are like programming languages that are used in computer science. Those are examples of artificial languages. But now what's interesting about this is that a lot of the theory that was developed for language by linguists before computer science, a lot of that theory carries over to computer science. And because computer science is a discipline that uses languages, each level of abstractions in a computer system has a language. And so language theory is a big part of computer science because when we program in computer languages. And so linguistics is actually a really big field, and there's a very close affinity with computer science and linguistics. So we obviously will be concerned more with artificial languages than with natural languages. So now, first concept, every language has an alphabet, right? And the Cyrillic alphabet is different from the English alphabet. So these, and an alphabet is, so what is an alphabet? An alphabet is a non-empty set of characters. Okay? And now, what do you do with the characters of an alphabet in order to make a sentence in the language? What do you do with them? You put them together. You place them next to each other. That operation is called concatenation. Okay? So concatenation is joining characters to form a string. All right? So that's the basic operation in languages or in linguistics, is how you join characters together to form a string. And not only that, but you can join characters together to form a string that makes a word, and then you can concatenate strings, which are individual words, together to make a sentence. Okay? And then a special string is the empty string, and the empty string consists of a concatenation of no characters. So that's kind of like the zero of this operation. Now, okay, so now here is a picture of, or not a picture, but a list of all the letters in the C++ alphabet. So when you write a program in C++, what are you doing? You are stringing together concatenation of all of these characters. You see what I mean? And look, they're all there. All the lowercase letters, the uppercase letters, the equal sign, the plus sign, the ampersand. So you can put ampersand, ampersand. You can concatenate those to make the and operator. And so there is a list of all of the letters in the C++ alphabet. Now let's think a minute about what you do when you write a C++ program. When you write a C++ program, you have this alphabet, you string them all together, and if you've strung them all together correctly and you submit it to the compiler, there will be no errors, right? But then what is the output of the compiler?
Assembly language?
Yeah, it could. Oh, let's say that it. Let's say that it goes to assembly language. So let's say that it compiles down to assembly. But now tell me this: what is that assembly language program consist of?
An alphabet and a string.
Yeah, it's just another string of characters. So what is translation when you're talking about translating from one language to another? You're talking about translating a string of characters to what? Another string of characters. So you have one string of characters on the input and you have another string of characters on the output. It's just symbol manipulation. It's those symbols, those characters, you know. And this alphabet, by the way, the C++ alphabet that we're looking at, these are called the terminal characters, okay, because they are what you see. These characters are the characters you see. And in fact, this next slide is the alphabet for the PEP8 assembly language, right? So here, it's a lot of the same characters. Are, you know, you've got uppercase letters and lowercase letters. Not quite as many symbols, or sorry, not quite as many like punctuation characters, right? So basically, what a compiler does is it translates a string of these kind of characters, and if it translates to PEP8 assembly language, it translates them to a string of these characters. That's all it is, from string to string, right? Now here's another alphabet. This alphabet is the alphabet for real numbers, okay? So, because what does a real number look like? Like, for example, 47.5. So this is what? 4 concatenated with 7, concatenated with period. See, the period is one of those letters of the alphabet. And then concatenated with 5. All right, so that's an example of a real number. Now, not all concatenations are legitimate sentences in the language, are legal sentences in the language. For example, if we said 4.7.5, this is not legal, nor is this 47.5. So this is not a legitimate, this concatenation, not all concatenations of characters from the alphabet are valid sentences in the language, right? And what you want to happen is, whenever you write a C++ program, you want your string of characters to be a legitimate, a valid sentence in the C++ language. So, like we said before, concatenation is the joining together of two or more characters to make a string, and you can also join together strings to make longer strings. And the empty string we're going to denote by the letter epsilon. Okay? So epsilon is the empty string, and now we don't have a binary infix operator for concatenation. Like, you know, we don't say 4 and then set concatenation with 7 and then another concatenation operator with point, you see. We don't have a symbol to do concatenation. We just put them next together, and it's really an infix operator. Concatenation is really an infix thing, right? Because you concatenate one thing with another thing. But the symbol is invisible. It's a binary operator, but we never see it because we just place the characters next to each other. But check out this concatenation property. What happens if you concatenate the empty string with any string x? What do you get?
That's string X.
Yeah, you get that string x back again. And it doesn't matter if you put the empty string with x or x followed by the empty string. In both cases, what do you get? Just that x. So what does that make the empty string?
The identity.
The identity. It makes it the identity element. And you're right? So you remember what identity means. Like, what's the identity for addition?
0.
0, because x plus 0 is x. All right, so here we have another operation. We have an identity element, the empty string. Okay, now you guys comes the big question, and that is, what is a language? Now, how do you make a valid sentence in the language? You concatenate all the what?
Letters of the alphabet.
All the symbols of the alphabet, you concatenate them together. Now, here's what you have to imagine. let's suppose T, here, let's suppose that T is an alphabet. So now, and what is an alphabet? It is a what of symbols?
A set.
It's a set. Yeah, it's a non-empty set. So it's a set. So now here's what I want you to imagine. T star is called the closure. Now, here comes a really important concept. What do we mean by the closure of an alphabet?
Subset of numbers.
Actually, it's not. It's more. It's a whole lot bigger.
All
It's
different operations that you can do.
No, it's the concatenation of all the elements on
yeah.
the stuff.
yeah, it is. Oh, so you guys are in automata theory. Okay. Yeah. Oh, good. So this is a review for some of you. Okay. So what happens is the closure is the set of all possible strings from the letters of the alphabet in that language. Now, I want you to realize how big that is. I mean, can you imagine that the string,
The string could be any size.
it could be any size. So this can, here's what's in T star. All the sentences of all the English language, of all the books in all the libraries, in all the history of the English language that have ever been written. All the collected works of Shakespeare, all the encyclopedias, all the Wikipedia articles
They have to be
in
valid
English.
sentences?
No. All of them. All of them, if you sat down monkeys and you typed at random, it would be all those, it literally by definition includes every single sequence of English letters ever concatenated together in all the world throughout all of history, and then it's even more than that. You can't write any string of English characters that's not in T star. It's huge, right? It includes the meaningless characters. You know, like here's one. So if you say see, spot, run, period. This is a valid sentence in the English language. But it also includes, oops. It also includes.
Get that off camera.
Yeah, I'm gonna have to say C, S, P, X, X, Y, exclamation, parentheses, asterisk, R, question mark. It includes this. Right? It includes all the meaningless. It includes all the meaningless ones. So it includes everything. But so now here's the question. What is a valid sentence in the English language? I mean, in terms of this T star.
Subject.
Now what is it? Now what's the word?
It's a subset.
It's a subset. See, not all of these. See, this is in the set. This is in the set. Sorry. Yeah, this is in T star. This is in T star. But this one's not in the language, but this one is.
So language is a subset of closure.
I couldn't have said it better myself. So the closure T star of alphabet T is a set of all possible strings formed by concatenating elements from T. And what is a language? A subset of the closure of its alphabet. So if I ever ask you, what is a language? What are you going to say?
A subset of
A subset of the closure of its alphabet. Right? So you guys, tell me this. How can we specify what makes a legal English sentence?
grammar.
Rules.
Well, I mean, yeah, one impractical way would be to just, because it's a subset, would be to what? Just list them all. But that's not practical. Why not? Because even the subset is infinite.
Subject verb?
Yeah, so you have to resort to something like subject, verb, yeah. You have to have rules. So, do you guys know, since you're in automata theory,
Grammar.
yeah. Here are 3 techniques to specify what makes a sequence of symbols a legal string in the alphabet.
I wonder which way we're going to use.
Yeah. So here are 3 techniques. And by the way, this is not this is not all of them, but anyway, we're going to look at grammars, and then we will look at finite state machines, and we will not have time to look at regular expressions, but there is such a thing as a regular expression that specifies the valid strings that are in the language, okay? All right.
We did all 4 in the computer science one.
Oh, good. Yeah. This should be.
What's the 4th one called?
Well, there are Turing machines.
Turing machines.
Yeah.
We talked.
Push down automata. Okay. So, good. So this will be review, but for the sake of completeness, we will review it. All right. So now here's one of those things. This is kind of like the. This reminds me of the von Neumann cycle. All right. What are the 4 parts of the von Neumann cycle? What's the von Neumann cycle? Fetch, decode, increment, execute, repeat. What are the 4 parts of a grammar? It's going to be a non-terminal alphabet. We'll denote that by N. A terminal alphabet. We'll denote that by T. A set of rules of production. We'll denote that by P. And the start symbol, which is an element of N. Okay? Now let's talk about each one of these individually. The first one, the non-terminal alphabet, is not what we looked at in the previous slide. The previous slides we looked at those alphabets that we were looking at. Those were examples of T. Okay? So those were called the terminal characters. So now N are non-terminal characters. So now a non-terminal alphabet, you never see elements of N when you actually look at a sentence. For example, let's take a look at this sentence right here, at this English sentence right here. Say, see spot run. Now, one of the rules that you could have in English that would specify what a valid English sentence is
Letter. The capital letter.
oh yeah, the punctuation. Oh yeah, that gets complicated with uppercase and lowercase letters too. I was going to say, actually, let me think of another one.
Subject verb.
Let's do this. Let's say because that's a command. Let me do something that's simpler. Let's say the fast runner won the race. All right. So here's a sentence, a valid sentence in the English language, right? The fast runner. Now you would never see, and this is what you would read. Now one of the rules of English grammar might be, well, you have to have a verb, and you have to have a verb, and you have to have a noun, which is the subject. All right. Okay. So what's the subject? What's the noun? What's the noun in this?
Runner.
The subject.
Runner.
Runner. Okay, but you would never see this. You would never see this. The fast noun. And then what is this? That's a verb. You would say. You wouldn't write this. These are not visible. This has a noun in it, and it has a verb in it, but this is an example of the non-terminal alphabet. So this is an element of N. You see what I mean? So this is an element of N. Right? But the letters that you see are R-U-N-N-E-R. You never see bracket, N-O-U-N bracket. Even though it's there. So you see, it's there sort of in the background. Do you guys still, do they ever teach diagramming sentences?
Diagramming didn't high school.
Oh, you did that. Because for a while they didn't do that. They did that when I was going in I can remember doing it in junior high. But then for a while they got away from all that. They wanted it to be holistic, blah, blah, blah. So they're going back to that, I guess.
I did in my class.
Yeah, so yeah, I thought it was, I always liked doing
Me
that.
too.
Yeah. The other thing that I really, with languages is when I started to learn a foreign language, that's when I learned a whole lot more about the English language. I learned more, just as much English by learning German than I did learning German. Because oh, now you got to translate. So now you have to know the structure, what's a verb, what's an adverb, and so anyway. So these are elements of N, okay, and you never see them. All right, and then P is a set of rules of production, and S is the start symbol, and it's one of the N. It's not one of T, it's one of N. The start symbol is one of N. So here is an example, our first example then of a grammar. Now this grammar is a grammar, it's figure 7.1, that gives us the definition of an identifier in a programming language. Are you with me? So N consists of, the non-terminal alphabet consists of identifier, letter, and digit. Yeah? And then we'll just use a small example. T, the terminal alphabet, is A, B, C, 1, 2, 3. Okay? And then P, that's the set of rules of productions. Right? So here's the rules of and what shape does a rule of production have? It has a non-terminal and then an arrow and then a string of terminals or non-terminals. Are you with me? So here we have, and the way you pronounce that single arrow, here, the way you pronounce this is produces. It's a rule of production. So we say produces. Okay, now this is different. In a minute, we're going to see a double-stemmed arrow, and this you don't pronounce produces. You pronounce this derives. Okay, so this is derives. Okay, but notice it's the single arrow that's in the rules of production. It's the double arrow that's in a derivation. Okay, so what does it say? What it says, what the rules of production say, the first rule says, an identifier produces a letter. And the second rule says, an identifier, or there's an alternative. These are alternative rules. And then another rule is, an identifier produces an identifier concatenated with a letter. The third rule says, an identifier can produce an identifier concatenated with a digit. So the operation there is concatenation, right? And then a letter can produce A letter produces B, a letter produces C, digit produces 1, digit produces 2, digit produces 3. And then what did we say S was? An element of N. So there, notice that S equals the identifier, and if you look up there at the top, identifier is one of the N's. Are you with me? Is everybody clear? So now, here's how this works. The way it works is this. What you do in order to derive a valid identifier, you start with a start symbol and you apply those rules of production in a sequence of derivation steps. Each time you go through, you use a rule to substitute using that rule. And then when you get in the end with all terminals, you know that is valid. That's how it works. So let's derive a few identifiers. So what do we always start with?
Identifier.
In this case, in this example, identifier. So we start with identifier. And then, now, this is going to be produces, right? So now,
That's derives.
sorry, derives. This is going to be derives. So an identifier derives, but now what does it derive? Now what we do is we pick one of these rules that has identifier on the left-hand side, because we're starting with identifier. So let's pick one. Which one do you want to pick?
Identifier digit.
Okay, so this do. Identify. Let me abbreviate, okay? Ident. Digit. And now what happens is, on the next derivation step, we can pick either one of these and pick one of the rules. You see what I mean? So which one do you want to pick? Identifier or digit?
Identify.
Okay, so identifier. So let's pick another interesting identifier rule. Oh, and by the way, this was rule what?
3.
This was rule 3. So here we put rule 3.
Let's do root 2. Root 2.
Okay, so let's do rule 2. So that means that we take this identifier and we change it to, we substitute identifier by a letter, right? So this would be ident letter, and then we bring down the digit. All right? And so this is rule what? That's rule 2, right? And now we just keep going until we get to all terminals. Well, can we get there pretty high?
Yeah.
Tell me what to do next.
Letter.
Letter A.
Okay, which ident? Oh, this ident?
Ident.
Oh, you want to do letter? Yeah, let's do letter. Okay, so this would be ident, and then this would be A, and this would be digit. Everybody, are you with me here? And that was rule what?
4.
Rule 4. And then, what's another one?
Ident.
You want to have this ident be a what?
A letter.
Letter.
A letter, so this would be letter. And this would be A, and this would be digit.
Rule 1.
Rule 1. Okay. And now what?
B.
You want to have this be B?
Yeah.
So B, A, and then digit.
Rule 5.
And that's rule 5. And then what?
BA2.
Okay, BA2. And that's rule 8. And now it's a string of all terminals. So we're done. So what does that say? That says we have just proved that BA2 is a valid identifier. That's what we proved by this derivation. Okay? Now, there's two things that we have to draw from this. The first thing that we need to draw is what's called the syntax tree. Okay, now, this sequence that we did by substituting using each rule of production in a substitution in a derivation to get a valid sentence. This can be illustrated by what's called a syntax tree, and the way a syntax tree works is like this. You start with the start symbol at the top. So over here, we start with identifier. And then what happens is each time we use a rule, we take this one that we're using the rule for and it spawns children at the next generation. So what rule did we use for the first one? We used rule 3. And rule 3 says what? An identifier produces a what?
Identifier and letter.
So here we go identifier. And what was it? Identifier and
A digit.
and digit? So here comes digit. So do you see how that rule does these two branches to here, right? And then what? Then what do we do?
We branched identifier to identifier and letter.
And so we did this to ident and letter. Then what do we do?
And then letter goes to A.
And then we did letter to A, so we'll just go right down to A. And then what?
And then identifier to letter.
Identifier to letter. And then
letter to B.
we did letter to B, and
Digit to 2.
and we did digit to 2. Now, do you see that this tree doesn't tell us what order we did things in over here? And in fact, we could have done the substitutions in a slightly different order and come up with the same thing. But what happens is the way you read this, the sentence that you read is, it's kind of like, you know, it's doing a what would this be? A pre-order traversal?
In order.
Well, I mean, it's all 3, actually. It depends on whether you visit it here, because you see this ident, we hit this ident 3 times. We hit it pre here, then we hit it in here, then we hit it post here. Do you see what I mean? So this actually applies to all 3 traversals. It just depends on where you want to say, you know, hit this. But in doing this coastline thing, you know, if you start from the left and you come down here and you go here, and then we end up coming up here, then as you encounter the leaves, which are the what?
Terminal.
The terminals, that's the string BA2, right? So this is BA2. See, we come down here, BA2. So that's the terminal string here. Yeah? Does everybody see that? Okay, so that's one thing. Now, well, actually, I think I'm going to save the second one for a few minutes later. Okay, so here's another grammar. That is grammar for the, what does this look like? Can you tell what this, oh, this is interesting because it has an empty string, an epsilon.
Gives you a number.
Yeah, what is it, can you tell what that is?
Is it like a negative or a positive D? No, D.
Or it could be D or, yeah, can you tell from the
You can have
rules?
multiple Ds.
Yes.
It's
Yeah, actually, look at that.
minus.
Yeah, here, give me some valid ones. Give me the shortest valid one. The shortest valid one is D. Okay, what's another, how many ones can have two terminal characters? You could have plus D,
Minus D.
you have minus D.
Epsilon D.
Ooh, epsilon D is what?
D.
That's D.
Yeah.
Okay, but is there another two-digit one?
D.
Yeah, DD. I think that's all the two. Oh, good. So now, so it sounds like everybody can go through there and see by, I mean, I don't have to derive these, right?
Integers.
Yeah, this is like signed integers. If D represents a digit, it's like a signed integer. Optionally signed.
Yeah.
Well, yeah.
Because then otherwise it's just assumed to be positive.
Right, but yeah, okay. And then if we wanted to, we could say D, instead of having, in this particular example, D is a terminal.
We could make
We could have D be a we could have uppercase D be a non-terminal, and then we could have D be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, you know, in which case but just to keep it short. Is everybody clear on how this grammar works and how it produces strings like this? And of course, you know, you can have plus D, D, or minus D, D, or D, 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 you know, and so on, etc. All right? And I won't bother. I think it's easy for you to figure out how to do the syntax tree. All right? Now, what's interesting about both of these grammars is the shape of each production rule. Because look, here is one grammar. It has production rules that look like that. And that previous grammar had production rules that look like this. Now, what's one characteristic that you notice that's interesting about these two grammars? What is always on the left-hand side of the production arrow?
Non-terminal.
How many?
1.
A single non-terminal. Right? Now, if every production rule has a single non-terminal on the left-hand side, do you know what that's called?
Context free.
That is called a context-free grammar. Yeah? Okay, so here, a single non-terminal on the left side of every production rule means that the grammar is context-free. And so, context-sensitive means what?
More than
Not context-free. Okay? So if it's not context-free, that means at least what?
it's context sensitive.
Well, I know it's context-sensitive, but what has to be the...
At least one production rule.
has to have what?
either
More than
a
non-single
terminal
non-terminal.
or more than one non-terminal.
Yeah, it can't... Yeah, there has to be one that doesn't just have a single non-terminal on the left-hand side. Are you with me? So, here is an interesting context-free grammar. Now here, let's experiment with this. I think this is a fun one to experiment with. Yeah, oh wait, did I say context-free? Sorry. Yeah, this is a context-sensitive grammar because, look, I mean, which does Rule 1 make it context-sensitive? No, because that has a single non-terminal on the left-hand side. But what makes it context-sensitive? Rules what?
3 through 6.
3, 4, 5, and 6. Are you with me? Now, here, let's derive the shortest string. This is figure 7.3. Let's derive the shortest string from this grammar in figure 7.3. So what do we start with?
It'll be, you start with A, so
We start with A because, yeah, because S down there, the start symbol is A. So we start with A. So here we go. Here goes, and that's capital A? So that's A. Oh, and yeah, I guess we're using capitals for non-terminals. And, okay. So A derives, now,
Rule 2.
rule 2
For the smallest.
for the smallest. So that would be what?
A,
Little a,
lowercase b,
little b,
big KC,
big C, and that's rule what?
2.
Rule 2.
And that derives with 5. Rule 5.
And this derives with rule 5, what?
All lowercase ABC.
A, B, C. Okay, and we're done. All right, so now we know that ABC is in there. Now let's do the next longer one.
The next longer one?
Yeah. So we would start with A. Now,
Goes to
A, B.
let's use rule 1. So it's little a, what is it? Big B, big C, and that's rule 1.
Then rule 2.
Is that right?
Yeah.
And then, and now let's use rule 2. So what would that be? Let's say little a,
Little A,
little a,
little B,
little b,
Big C.
big C, big B, big C.
big C, big B, big C, and that's
Big B.
Rule 2.
that's rule 2. Did I do that right?
Yeah. Now rule 3.
And now rule 3 will let us do what?
Switch to
Switch to CB.
Okay, so here, little a, little b, big B,
Big C, big C.
big C, big C, and that's rule what?
3.
That's rule
Now we can do rule 4.
3. And now rule 4 lets us do what? Does that let us change this big B to a little b?
Yeah.
Okay, so this implies. So this drives little a, little b, big C, so that's rule 4.
Rule 5.
And then rule 5, what does that let us change this big C to a little c? If it, okay, so here, so this is little a, little b, little c, big C by rule 5. Oh, good grief, this is going to be 1, 2, 3, 4, 5, 6. And this is going to be little a, little b, little c, and that's rule what?
6.
Rule 6. And now this is, yeah? Now, can you tell?
That was planned?
Well, I mean, I don't know about
What the
that.
next one will be?
Yeah, can you tell what it would be?
It'll be 3 A's, 3 B's, 3 C's. All lowercase.
Yeah, and could you ever, yeah, that's right, it will
Yeah.
be. You can derive little a, little b, or you can derive AAA, BBB, CCC. Can you derive this? Is it possible to derive AA, BB, CCC?
No.
Why not?
Because
Because you can't.
the only
Why not? Can you argue? Can you give an argument of what? Can you?
Because every time you say you generate an A, you have to generate a B and a C as well. So you can have,
And eventually, what happens to each uppercase letter?
it gets dropped down to lowercase.
It gets dropped down to a lower. So you can use that observation.
The
There's
protections
no way to
don't allow
create
it.
another letter. Because anytime you have 2 C's, it goes to 2 C's. You never have a way to get to 3 C's from only 2.
Right, right. The only way that you can create a longer string is with rule
Hey.
1. Yeah. And furthermore, and do you see why this is called context sensitive? Look, whenever you take something out of context, if somebody accuses somebody else of saying, well, you quoted me, but you took me out of context. What is that? What are you complaining about?
the other things were important.
What other
Yeah,
things?
context.
What other things?
That was left out.
Other words.
What do you mean that?
The things in context.
What does that mean?
The words. The characters. The.
If
Being
information. But what information are you? If you quote somebody out of context, what are you? Why are you complaining about? You took that statement out of context. What does that mean? But
It's
what?
context sensitive.
Yeah, your remark is context sensitive, but why is that, why? What does it mean to take it out of a context? It means you said just what I said, and not what?
All.
What I meant to say?
No, it's not that you have to devise, good into my mind and what I want to say. It's that
It
you're,
doesn't follow the rules.
no,
It changes it?
no, come on, you guys.
I'm so confused.
Now, I'm just trying to ask you in English, when you, suppose I come up to you and I said, you quoted me out of context, and I'm complaining to you that you quoted me out of context. Why am I, what's my complaint that you did? What did you do when you quoted me out of context? You said exactly what I said. And I say, yeah, that's what I said, but you're taking it out of context. What did you?
Said more than that.
You didn't take into account everything around what you said.
That's what it is. It's that you didn't take into account what I said before and what I said afterward to give that more meaning. Are you with me? So it's when you leave out what comes before and what comes after. Do you see what I mean? That's what context means. Right? So yeah, it's other information, but what other information? It's the information that's surrounding. So look, do you see why is this rule 3 a context sensitive? No, wait. Is this rule 4 a context sensitive rule? Now, and what does rule 4 say that you can do? What did rule 4 say we could do, you guys?
You have a little b
Take a
right before a
BB
big
and make
B.
the...
It says you can take a big B and change it to a what?
Little b.
A little b. Well, then why don't we just have a rule like this? Big B produces little b.
Because there has to be a little b right before it.
Yes, you can only do this in the context of having a what? A little b before it. If you had a rule like this, it would be a different language. Are you with me? So, and you see what I mean? It's and here, what about this C? What did this rule 5? What did this rule 4 say? It said you could change what?
Big C, a little
A big C to a little c. But only if what?
Yeah,
A little bit.
But only if there's a little b in front of it. So it's in the context. You can do this, but only in the context of being after a little b. Do you see? Yeah. And now what's interesting about this is that, what about drawing a syntax tree? It's actually, you can't do it.
You can't with sensitive ones?
Well, I don't think so. I mean, how would you do
You
it?
just look at what branches are on the same level.
Because you have to, because this is the single thing that's on the left of the,
Yeah.
this is the single thing that's on the left.
Yeah,
You see that's on the left of the production rule,
makes sense.
right? So it's very difficult. I think I saw somebody who actually had a way to, some complicated way to visually represent that. Okay. Now, let's get back to get back to our original problem. So now what we know is we know how to derive a valid sentence. Now let me ask you a question. What does your compiler do? Or what is your assembler going to have to do? Whenever you run your assembler, are you going to say, give me a valid assembly language program?
No.
What are you going to do?
Make sure it's valid.
Check to make sure it's out.
Yeah, what do you give it? You give it a string of what?
Okay.
Yeah, what kind of characters? Terminals or non-terminals? You give it a string of terminals, and what does it do?
Just to find out if it's valid.
It has to find out if it can be derived.
reverse.
It's doing the reverse of what we did. So does everybody understand that? That's basically the difference. So here there's two different problems. So here in figure 7.4, what we did is what we have been doing is we have been deriving valid sentences. We've been doing part A. Are you with me? So what we did is we said, given that we have this grammar, we can produce a derivation. We can do a derivation given this grammar, and what comes out of that derivation is a valid sentence. But that's not what a translator has to do. What does a translator have to do? It's given the grammar and a proposed sentence. And it has to be able to determine whether or not it's valid. And if it is valid, it has to produce the derivation. Does Does everybody see that? It's a fundamentally different problem. It's not just producing one at random. It's given this, can you produce it? And furthermore, if you can't produce it, you have to know that it can't be produced. Or derived, rather, sorry. Can't be derived.
Is our assembler going to have to do outputs for errors and things?
Mm-hmm.
Like what kind of error
Mhm.
and why it's wrong?
Mhm. You have to have a way to do that.
Great.
Okay. So here is a grammar for here's a grammar for expressions. Oh, do you remember what an expression is from formal methods?
Use an expression.
Oh my
No,
God.
if an expression is
Use an expression.
well, no, it's either the first one. It's either what?
Variable?
It's either a constant or a variable, and then if
Unary or
If you use
is an expression,
The
then
parentheses expression.
yeah. Okay, now no, what is that one?
parentheses.
No, what is that one?
5, rule 5.
That's rule 5.
Right.
Are you with me? Are you with me? And then what was one of them? If
Unary.
binary. I think this only uses binary.
Binary.
Okay. So then if E is an expression and
And F is an expression.
F is an expression, then T star. Well, T is going to be T stands for term.
Yeah.
Okay. But the start symbol is an expression. Are you with me? The start symbol is an expression, and the non-terminals are expression, term, and factor. Okay, so the F is factor. And then the T, the alphabet is plus, star, left paren, right paren, A, and P are these production rules, right? So here, let me ask you this. Do you think this, A plus parentheses, no, let me do A times parentheses A plus A. Do you think this is valid?
Yeah.
Okay, now, one way we could do it is to do a derivation. It's a little quicker to do the syntax tree. Can we do the syntax tree for this? What do we start with?
E.
We start with E, and what do you think we should do?
E plus T.
No.
I'd say go E
E
to T.
times.
I think the times first, right?
Yeah.
But how can we get the
No, no.
time?
E to T, T to T times
Yes.
F.
Yeah, E to T,
So T times F.
T to T, now notice here, times F,
Oh, I do remember doing
T
this.
to F.
and then what?
A.
This T to F,
And then F to A.
to A,
F will go
and then
to
F will go to what?
parentheses
F will go left paren, E,
E, and then
right paren, and then this E will go to what?
E plus T.
So this will go 3 again. So this would be E plus T,
E goes to T.
and then E will go to T, T will go to F, F will go to A, and this T will go to F, which will go to A.
I
Right?
remember this exactly.
Yeah, well, it's because it's you keep using the same examples over and over again in the different courses. Anyway, right? So do you see how this is A times A plus A, A times paren, A plus A paren, and that's it. Yeah? Is that this? I think this is slightly different. What expression is this?
A times A plus A.
Parentheses
Yeah, A times A, parentheses A times A, parentheses plus A. Yeah. And here's an example of the syntax tree for
DD.
DD, which is that here. This is a syntax tree for this, right? Notice how it has the empty string in there. Okay? And now you guys, for C++, do you know what the start symbol for C++ is?
Translation unit.
Translation unit.
Oh my.
Wow.
So here it is. There's the and what is that vertical bar?
I don't know.
That means or. So that's actually 2 rules. That first rule is actually 2 rules. Its translation unit produces external declaration, and then another rule is translation unit produces translation unit concatenated with external declaration. So it's just a shortcut so that you don't have to keep writing.
We have a whole list
And here it is, yeah, here it is. And then what each one of those is another one, is another one, is another one. And look at do you see the terminals? Void, char, int. Okay. And then here is, and then statement, da-da-da, and there's the semicolon. There's the if and the paren and the else, the terminals. Are you with me? Boom, 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 boom. There's some declaration list. Boom, 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 boom. Boom, 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 boom. Boom, da boom, boom, boom. And then there's the letters and there's the digits. Finally, the terminals, right? Oh, and there's identifier. What's an identifier?
A letter.
A letter or what? Identifier followed by a letter or what? Now, C++ actually has the grammar. You can look it up online.
Oh.
There is a grammar for C++. And this is I just abstracted. This is just part of it.
Condensed.
This this is not the whole C++ language. This is a subset of the C++ language. But here is, you have an assignment for next time to do a parse. Here is an example of what the while statement is. Here, can we write down what that is before we quit?
While, paren,
Yeah, so it's while. Here, let's do it. So it's while
paren, A is
Paren.
less than or equal to 9.
less than or equal to
Close paren.
9.
That's
Is there a brace or no?
There is no brace.
No brace? Okay.
S1.
S1 semicolon.
Statement.
That's just S1 semicolon, right? And assuming, and this dot 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 means assuming that S1 is a statement.
Right.
So that's how you would parse it. And guess what? Every time you submit a C++ program to the compiler, it does that automated. It does that automated. That's what compilers do.
Is that what assemblers do?
That's what your assemblers, well, we'll talk about that later.
Okay.
All right, good deal. See you next
A
time.
little simpler.